Good day. We are back for another face-to-face meeting for Stat 151. Today we are working on section 4.2 in the textbook, which is continuing our study of bivariate distributions with discrete random variables, this time focusing on the covariance, correlation, and the least squares line that gives the best sort of fit to the distribution of. So we are going to, there were a number of questions on the discussion board, but I think that the best way to address them is really to do a really thorough example, which I hope will help people understand sort of how to work with these distributions better, how to calculate expected values, variances, covariances, and kind of remind us of a few things along the way. So I'm going to start with my example. So this is not one from the book, it's one that I made up this morning, but we're going to consider a game in which I roll a four-sided die twice. I roll the die the first time and I observe the number that lands facing up, and X is the number that lands facing up on the first roll. I'm going to roll the die a second time afterwards, and if the number that lands facing up on the second roll is greater than X, which remember was what I rolled the first time, then the player, the number of points the player wins is equal to the number that landed on that second roll. If the number that lands facing up on the second roll is less than or equal to the first roll, then the player doesn't earn any points. So Y is going to be the number of points the player earns. So I'm going to go through and I'm going to do each of these things. I'm going to graph the support of X and Y and show that the joint probability mass function, define it on that support. I'm going to do that on a graph because there's a question of how do I do this on a graph. So I'm going to go through and do that. I am going to show the marginal distributions of X and Y in the margins. I am going to find the mean of X, the mean of Y, the variance of X and the variance of Y. Then I will find the covariance of X and Y and the correlation for X and Y. And then finally I'll find the least squares line and show it on the graph. So kind of go through a full example with all the things that we've been doing. Okay, so the first thing I need to do is I need to draw the support of my probability mass function. Now remember here, X is the number on the first roll, Y is the points earned. Since it's a four-sided die, I can roll a 1, a 2, 3, or a 4. Those are my possible values of X. And since the points earned is going to be equal to what's on the second roll, if it is greater than the first, the sort of possible values here are going to be, if I look at it, really I'd have to be more than 1, right, because I couldn't roll. If I roll 1 the first time, if I roll 1 the second time, I'm not greater than that. I have to roll at least 2 to be greater than my first roll. So I'll draw them all. 2, 3, 4. So I'm just kind of thinking about what could happen. I could roll a 1 on the first roll and a 1 on the second roll, in which case I would win 0. I could roll a 1 on the first roll and roll a 2 on the second roll, in which case I win 2. I could roll a 1 on the first roll and a 3 on the second roll. In that case, I win the 3 that I rolled on the second roll. And I could roll a 1 and then a 4, and I'd win 4. Right. And there's a 1/16th chance of each of these things happening. Now if I roll a 2 on the first one, I could roll a 2 on the first one and a 1 on the second one, in which case I wouldn't win anything. I could also roll a 2 on the first and a 2 on the second. Again, I wouldn't win anything. So there are 2 out of 16 possible ways that I might roll a 2 with the first die and end up with 0 points. I could roll a 2 and a 3, in which case I would get 3 points. That would happen 1/16 of the time. And I could roll a 2 and a 4 and get 4 points, which would happen 1/16 of the time. Continuing on, thinking about possible outcomes, I could roll a 3 on the first and a 1 on the second. Since the 1 would be less than 3, I would win 0. I could roll a 2 on the second and a 3 on the first. Again, I would win 0. And I could roll a 3 and a 3, and again I'd win 0. So 3 out of the 16 possible outcomes involve me rolling a 3 the first time and earning 0 points. And I could roll a 3 the first die and a 4 on the second, in which case I would win 4 points. That would happen 1 out of 16 times. And then if a 4 is rolled on the first die, there is no chance that I'm going to roll something bigger on the second die. So I'm definitely going to win 0 points in that situation. It could happen 4 different ways. I could roll a 4 and a 1, a 4 and a 2, a 4 and a 3, and a 4 and a 4. So the probability associated with that is 4/16. So just looking, this is our graph of our support for f of x and y, and it also shows the probability mass function on that support. Now the next thing we want to do is show the marginal distributions in the margins. So what it means by in the margins is, okay, just using what we have here, using our graph. So we've got values of x here, and we want to show what the marginal distribution is next to it. Now remember, to find the marginal, what I want to do is I want to add, for all the times when x is equal to 4, add up the probabilities that are associated with all of the possible outcomes. So here, with 4, there's only one possible outcome in the support, and it has probability 4/16. I'm going to zoom just a tiny bit. With 3, I've got 2 possibilities. I could have 3/0, which has 3/16, and 3/4, which has 1/16. So if I add those together, I get 4/16. Here, if I roll 2 on the first die, I have 1/16 plus 1/16 plus 2/16, again gives me 4/16. And finally, if I roll a 1 on the first die, 1/16 plus 1/16 plus 1/16 plus 1/16, 4/16. So all of these are equal to 1/4. And this makes total sense, right? Because we've got a 4-sided die. If we're not caring about what happens with the second die and how many points I win, then what's the chance that I would roll a 1? It's 1/4. What's the chance I'd roll a 2? 1 in 4. 1 out of the 4 sides is going to have a 2. So the marginal distribution just shows us what the probability would be that each of these values of x would occur if we don't think about the value of y. Similarly, we can add across to find the marginal distribution of y. 1, 2, 3/16 is the probability that y equals 4. 2/16 is the probability that y equals 3. Whoops, I didn't mean to draw that all the way through. 1/16 is the probability that y equals 2. And there's no chance of having 1, but a 4 plus 3 is 7, 10/16 chance that y will take on the value 0. So those are our marginal distributions of x and y. And the next thing I want to do is I want to find the means and the variances of x and y. If I want to find the mean of x, which is the expected value, remember, of x, there are two ways that I could do this. I could take all of my xy pairs that are in the support of x, of this probability mass function for x and y, and I could multiply x times f of xy for all of those xy pairs. So in this case, I'd say, okay, well, I'd have 1 times 1/16 plus 1 times 1/16 plus 1 times 1/16 plus 1 times 1/16 plus 2 times 2/16 plus 2 times 1/16, and so on. This is equivalent, though. If we already have our marginal distribution, it's usually easier just to look at all of the values of x that are in the support of x and to take x times our marginal, which is exactly what we're doing back in Chapter 2 when we're finding expected values. We're just taking the PMF. Really, this marginal PMF is the PMF for x, right, if we looked at it separately from y. So my mean is going to be 1 times 1/4 plus 2 times 1/4 plus 3 times 1/4 plus 4 times 1/4, and that's going to give us a mean of 2.5. Now if I want to find the variance of x, the easiest way to work with it is to say, okay, well, it's going to be the expected value of x squared minus the mean of x squared. The expected value of x squared, this is a function of x, so I'm going to sum for all the x's in the support of x, x squared times the marginal probability that x is equal to x. So that's going to give me 1 times 1/4 plus 2 squared times 1/4 plus 3 squared times 1/4 plus 4 squared times 1/4, which gives me an expected value of x squared equal to 7.5. And now to find the variance of x, I can take excuse me, my expected value of x squared minus my mean of x squared, which gives me 7.5. My voice is crazy now. Minus 2.5 squared, which gives us a variance of x equal to 1.25. So that's how we can find the variance of x. We can do the same kind of process to find the mean and variance of y. The mean of y, I'm going to use my marginal distribution because it's usually easier if I have it. Y times the marginal f sub y of y. So I get 4 times 3/16 plus 3 times 2/16 plus 2 times 1/16 plus 0 times 10/16, which gives me a mean that is equal to 1.25. To find the variance of y, I'm going to first find the expected value of y squared and then subtract off the mean of y squared. The expected value of y squared, I'm going to go through all the y's in the support of y. I'm going to take y squared and multiply by the marginal probability that y is equal to y. So I'll get 4 squared times 3/16 plus 3 squared times 2/16 plus 2 squared times 1/16 plus 0 squared times 10/16 gives me my expected value of y squared equal to 4.375. And now my variance of y, sigma squared of y, is my expected value of y squared minus the mean of y squared, gives me 4.375 minus 1.25 squared. It gives me a variance of 2.8125. So that's how I can find the means and variances of the marginal distributions. Now, as I say, we could do all of these things by summing over all the xy pairs, but when we have the marginal distributions, it's just much easier, has a lot fewer terms to add up if we use the marginal distribution when we do it. Okay, so the next thing I'm going to do is I'm going to find the covariance of x and y. Okay, so the covariance of x and y is equal to the expected value of x times y minus the mean of x times the mean of y. Now we know the mean of x and the mean of y, but we need to figure out the expected value of x times y. Remember that anytime we have a function of x and y, if u is a function of x and y, to find the expected value of u, I'm going to sum over all the xy pairs that are in my support of my PMF. I'm going to evaluate my function for each of these xy pairs and then multiply it by the probability mass function, little f of xy. So in this case, my u of xy is equal to x times y. So my expected value of x times y is going to be the sum over all of these xy pairs in the support of x times y times little f of xy. And it does turn out to be, a fair amount of multiplying and adding up terms. So let's see. Let me grab my probability mass function again so I can take a look at it. Maybe I'll scooch it this way. Okay, so I've got 1, 0. So I've got 1 times 0 times the f of 1, 0, which is 1/16, plus 2 times 0 times the f of 2, 0, which is 2/16, plus 3, 0, 3 times 0 times the f of 3, 0 is 3/16, plus 4, 0, so 4 times 0 is my function, and then there are 4/16 is the probability mass function at that point. Plus, here's my next value in support. That's x is 1, y is 2. So I take 1 times 2 times the probability mass function evaluated here is 1/16. Plus, go to my next point here. I've got 1, 3. So 1 times 3 times my f of 1, 3 is 1/16, plus I've got 2, 3. X times y is 2 times 3. Probability of that pair is 1/16. plus, and I come back up here, 1, 4. X times y is 1 times 4 times 1/16 plus 2, 4, so I take 2 times 4 times 1/16 plus 3, 4 times the probability mass is 1/16. And if I go through and do all of this multiplication and addition, I get an expected value of x times y equal to 2.1875. Now to find my covariance. I'm going to take my expected value of x times y minus the mean of x times the mean of y. This gives me my 2.1875 minus mean of x was 2.5, mean of y was 1.25, and it gives me a covariance equal to negative 0.9375. So that would be my covariance. Now the correlation, so the covariance gives me a sense of sort of how, in what way the variables are related. When I have larger values of x, I would tend to have smaller values of y, right? The larger my first roll is, the less I'm likely to win. But the correlation gives us a way of sort of being able to judge how strong that relationship is on a scale, on a numerical scale, where we have a range going from -1, which would be a perfect negative relationship, to a positive one, which would be a perfect positive linear relationship between them. So correlation, then, we take our covariance of x times y and divide it by the standard deviation of x times the standard deviation of y. And as Stephen pointed out on the discussion board, be careful not to divide by the variances. You want to divide by the standard deviations multiplied together. So our covariance we just found is negative 0.9375. We need to divide by the square root of our variances. So the square root of the variance of x, let's see. The variance of x was 1.25, so that's the square root of 1.25. Variance of y was 2.8125, so I'm going to multiply by the square root of 2.8125, and that gives me a correlation that is equal to negative 0.5. Now the very last thing I was going to do is to look at how we can find the least squares line for these values. The line of least squares is given by the formula y equals the mean of y plus the correlation times the standard deviation of y divided by the standard deviation of x times x minus the mean of x. And that was derived in the textbook. So in this case, we now know all of these values. We've calculated them all before. So it's just a matter of substituting them in. The mean of y, let's see, is 1.25 plus our correlation is minus 0.5. Sigma y is the square root of 2.8125. Sigma x is the square root of 1.25. x minus the mean of x was 2.5. If we simplify this whole thing, we get the least squares line equal to y equals 3.125 minus 0.75x. And if we want to add that to our original graph, I'm going to cross the y-axis at 3.125, so somewhere around here. I'm going to cross my y-axis a little bit past 4, somewhere down here. We're going to have a line that's going to kind of go through like this. Now this line, for some of you, and I'll just label this as my regression line, my least squares line is 3.125 minus 0.75x is equal to y. That's our line. Now, some of you who have taken Stat 111 and Stat 141 or another statistics course, this might look like a really weird fit to this line, especially because, you know, usually we think, okay, well, it should have the points close to the line. So why does it look like this? Well, the reason that it looks like this is because we have to consider that the weight that each of these points has is related to the probability mass function at that point. So these points up here have only weight of 1/16. These points down here has a weight of 4/16, 3/16, 2/16. So they're pulling this line down towards it, and that's really why we have that line that doesn't look like it fits very close to our points in our data, in our probability mass function in our support, but it is being sort of pulled by the higher weights down in these bottom parts. So if you thought, sometimes people look at these things and they think, that doesn't look like it could possibly be right. It is right, and the reason that it's right is because it's like you have 4 values here instead of just 1, and like you have 3 values sitting here instead of just 1, and so on. So those will have larger weight and tend to influence the line more. Okay, so that is my example for the day. I think it walked through just about all the things that you need to be able to do in this lesson, so hopefully it'll help review some of the topics from last time, like the marginal distributions and the means and variances for the individual x and y, but also help you calculate the covariance, the correlation, and the least squares line. Have a great week.